This is the Swiss cheese model presented by Andre Watson, Cameron Scribner, David Walk, and Joe Yang. Our case study is going to be on the Boeing 737 uh, recent air crashes. So the Boeing 737 is a historically significant twin-jet narrow-body commercial airliner that has been in continuous production for over 5 decades, becoming one of the best-selling aircraft in aviation history. Its latest generation, the 737 MAX, has become a central case study in modern aviation safety due to a series of high-profile accidents. The original series of the Boeing 737 was the Dash 100 and Dash 200. Development began in the early 1960s to meet the demand for short-haul jet transport, competing with aircraft like the Douglas DC-9. The 737 introduced underwing engine placement for easier maintenance and a wider fuselage, offering 6 abreast seating, which was a competitive advantage. The 737 was one of the first jets designed for a two-person flight deck, eliminating the need for a flight engineer and setting an industry standard. The first flight was in April 1967 and it entered service in 1968. The 737 Classic series consists of the Dash 300, 400, and 500. Introduced in the 1980s, these variants incorporated more fuel-efficient, quieter CFM56 turbofan engines, which required flattening the bottom of the engine nacelles due to low-to-the-ground wing placement. The series included longer fuselage options and featured updated avionics. The next generation or NG series consists of the Dash 600 through the Dash 900. Launched in the 1990s to compete with the Airbus A320, the 737 NG received a major redesign, including new wings, an updated flight deck, and a further range and efficiency boost. The 737-800 became a best-selling variant. The Boeing 737 MAX is the fourth generation of the 737 family, announced in 2011 to directly counter the fuel efficiency of the Airbus A320 Neo or new engine option by using new, larger, and higher bypass LEAP 1B engines and updated aerodynamic features, including new winglets. Key features of the MAX was the new engine placement. The larger LEAP 1B engines were placed slightly higher and further forward on the wing. This change affected the aircraft's pitch characteristics, giving it a tendency to pitch up during certain high angle of attack maneuvers. The MCAS system, the Maneuvering Characteristics Augmentation System, was to ensure the 737 MAX handled similarly to the previous 737 NG series, and thus avoiding costly full flight simulator training for pilots. Boeing introduced the MCAS software. This system was designed to automatically push the aircraft's nose down to counter the pitching tendency using data from a single angle of attack or AOA sensor.
Lion Air Flight 610, October 29th, 2018. Flight Lion Air 610, registration PK LQP, departing from Soekarno Hatta International Airport in Jakarta, departed at 6:20 a.m. local time, with clear weather, good visibility, and no cumulonimbus clouds. Everything seemed fine, especially reassurance after leaving maintenance operations the day before, where flight critical systems and the air data system, specifically the AOA sensors, have been serviced. As you see up here, we have one of the AOA sensors for an aircraft. Aboard piloting this new 737 MAX aircraft was Bairu Porboi, as recorded in the KNKT report, as the captain. He was 41 years of age and had a flight experience of 6,000 hours, which is around 4,000 hours less than FAA rated captains, which usually have a flight time around 10,000 hours. Serving as first officer, we have Harvanu, commonly referred to by one name. He was also age 41, with 5,000 hours of total flight time, with only 4 hours being on the max, and only 5 hours for the captain. After departing with 189 people on board, including 181 passengers and 8 crew members, Lion Air Flight 610 climbed to an altitude around 5,000 feet shortly after takeoff, before experiencing erratic altitude changes. Then the aircraft rapidly descended and then climbed again as pilots fought to regain control in a rapidly deteriorating situation. Here we have, this is supposed to be flight 110, that's its flight data right there showing its altitude and airspeed changes. Ethiopian Airlines Flight 302, which happened on March 10th, 2019, tail number ETAVJ, departed Adidas Abu Dhabi Bull International Airport, Ethiopia, at 8:38 local time, or 5:38 UTC, with a destination in Kenya. Around 18 days earlier, there were a variety of logbook write-ups, such as flight control problems and APU write-ups with minor electrical write-ups, but everything was thought to be cleared by the time Flight 302 departed. Aboard piloting this 737 MAX aircraft was Yard Getchwash with 8,000 hours total flight time and 4,000 hours total on all MAX variants, with around 100 hours on the MAX, slightly more experienced than the Ethiopian Airlines pilots. First officer or co-pilot Muhammad had a total flight hours of 361, which is extremely low compared to FAA or US standards, where you generally have to reach 1,000 or 1,500 hours of flight time before being able to fly it or pilot as first officer, with a total time of 207 hours on MAX variants and 56 hours on the MAX variant. Flight 302 departed without any immediate issues, carrying 8 crew members and 149 passengers. After climbing to an altitude of approximately 400 feet, air messages and oral and master caution alarms began to sound. The pilot struggled to control the aircraft and communicated with ATC for about 6 minutes before the aircraft ultimately crashed. Here we have some of the trajectory provided by the Kenyan and Ethiopian Flight Authority. Up here we also have where the fourth MCAS takeover happened and when the last MCAS takeover happened. Crash analyzation. Both Lion Air Flight 610 and Ethiopian Airlines Flight 302 were tragic accidents that didn't come out of nowhere. In both cases, there were warning signs before the actual flights, recorded in the aircraft logbooks and through previous crew write-ups, such as multiple write-ups for Flight 610 were made by flight crews about unreliable airspeeds and altitude indicators, as well as stick shaker activation, which is where the control stick in the cockpit shakes rapidly back and forth or side to side shortly after takeoff. These are classic signs of AOA disagreement. While Flight 302 on March 9th, 2019, the day before, the flight crew experienced erratic flight control behavior shortly after takeoff. The MCAS system was activated in response to a faulty AOA sensor, but the pilots manually trimmed and turned on the stabilizer trim cutoff switches, which cuts off the MCAS. Lion Air Flight 610 took off from Jakarta on October 29th, 2018, with 189 people on board. In the days leading up to the crash, the aircraft had repeated write-ups for unreliable airspeed and altitude indication. On the previous flight, the stick shaker had gone off right after takeoff, and MCAS had already tried to trim the nose down. The crew on that flight managed to fight it manually using cutout switches and landed safely. Maintenance was performed overnight, including replacing the AOA sensor, but the sensor installed turned out to be faulty. The next morning, Flight 610 experienced the same issue. Just seconds after takeoff, the stick shaker activated, oral and visual warnings went off, and MCAS repeatedly forced the nose down. For about 12 minutes, the crew was in constant fight with the airplane. Eventually, they couldn't keep up with the system, and the plane crashed into the Java Sea. This 12 minutes here includes the 6 minutes prior to the activation for its flight. Ethiopian Airlines on March 10, 2019 followed a similar pattern. The plane also experienced AOA issues the day before. The previous flight crew had to deal with normal flight control inputs but was unable to stabilize and land. Maintenance cleared the AOA vane but did not replace it. Next morning, Flight 302 took off with 157 people on board. At around 400 feet after takeoff, air messages and master caution started. The pilots were immediately overwhelmed with the MCAS nose down inputs and multiple alarms. After about 6 minutes of struggling to control the aircraft, the plane was impacted the ground at high speed. In both cases, the real issue wasn't just failure itself. It was that the system was allowed to fly again even after repeated warning signs. MCAS was poorly designed to rely on one sensor. The crews weren't fully trained on how it worked, and the faults recorded earlier were not resolved in a way that addressed the root cause. These accidents weren't random. They were the result of a chain of events: a faulty sensor, a flawed system design, poor communication, and gaps in training and maintenance. Those logbook entries before the flights tell a story that was ignored until it was too late. Not because the technicians didn't do anything about it, but because Boeing failed to equip and notify operators of a system that was flawed. The failure of the Boeing company. The 737 MAX was embarrassing as a company because they knew that the new updated MCAS system was going to require more training for pilots and engineers. Boeing was competing with the A330, which was a more fuel efficient aircraft compared to the previous generation of 737s. Due to this corporate greed and hush-hush agreements with test pilots, in both of these incidents, it was Boeing's failure to address the additional training required to fly the new 737. The sprint to get the 737 MAX out flying was 100% profit first, instead of looking for safety and efficiency with engineers.
Latent conditions are hidden systems that lie dormant until they align with active failures. In the case of the 737 MAX, these were embedded deep within Boeing's organizational, regulatory, and design processes. Organizational pressures such as production deadlines and frequent cost cuttings led Boeing to prioritize rapid development over thorough safety validations of its aircraft. Boeing decided to retrofit the MAX rather than do a redesign, introducing compromises littered through the aircraft. As we talked about in the crash analysis, a lot of these were covered, but a list of direct latent conditions are the MCAS was designed to rely on a single angle of attack sensor, ignoring redundancy practices. Delegated certification authority allowed Boeing to self-certify key systems, reducing the FAA's direct scrutiny on the 737 MAXs. Boeing assumed pilots could override the MCAS system without additional simulator training, which obviously played a massive role in both of the accidents that we talked about. If they were able to turn off the system, then they probably would have survived. No synthetic sensor model was used to cross-verify angle of attack data, leaving the system vulnerable to single-point failures. And these latent conditions formed the holes on the Swiss cheese model, which we're going to talk about now.
All right, here's the Swiss cheese model. So basically, a Swiss cheese is where basically there's layers of defenses and there are holes that penetrate. There are like failures that penetrate the holes, and if the holes line up, there will be a failure. So here's an example of visualization of what it will look like. So on the first layer of the cheese, which is pilot training and checklist, there is basically low or minimal pilot training with almost no specific instruction to the MAX aircraft because it was designed to operate similar to the previous 737, which is the 737 new generation, I believe. And there's the next layer of the cheese is AOA redundancy slash sensor fault, and basically in this hole, the MCAS relied on a single AOA sensor instead of using both, eliminating the intended redundancy in the system. And within the maintenance history, days before both flights, there were clear warning signs indicating issues within the AOA system on each aircraft, and the AOA was miscalibrated on previous repairs. Okay. Then the next holes within the system is certification. Boeing technical pilots had misled the FAA about how the MCAS functioned by downplaying its role. They avoided triggering extra training or deeper review, leaving a critical system less synchronized during certification. And there was a lack of FAA oversight to the Boeing organization designation authorization. Within the repair process, the repairs performed for both Flight 610 and Flight 302 were insufficient. For Flight 610, the newly designed AOA sensor was improperly calibrated, which left the issue unresolved. For Flight 302, maintenance involved only a sensor cleaning, but not a full inspection or replacement, allowing underlying problem to persist. Within the flight warnings and management trees, after the pilot tried to trim out the aircraft, MCAS will trim the horizontal stabilizer, which results in a mistrim of the aircraft, which leads to a total systems failure. Bingo bird! Fixing the cheese. So basically, we are blocking off the holes within the layers of defense. So within pilot training and checklist, there's revised pilot training to recognize erroneous stabilizer movement and effects of potential angle of attack failures. And Boeing added slash revised 8 new non-normal flight crew procedures to the airplane flight manual. AOA redundancy and sensor fault. So basically, AOA discrete alert is now standard. There's a single nose down command, which is not repeated. It limits MCAS movement to ensure sufficient pilot input, and it now, shocker, it now uses both sensors. With the maintenance history, there's improved system reliability, updated inspection program for the MCAS system, and AMS additions. Within the certification, recently, like the FAA has increased oversight at Boeing, but as of recently, in September, I believe now Boeing has some of the certification powers back. Then within the repairs process, introduce a final check to make sure there are no bias was introduced to the AOA sensor after replacing the sensor, and operator must test the AOA sensors before it returns to service. And finally, the last layer of fixing the cheese. Boeing implemented a cross-flight control computer, which is the FCC, Trimbuller, which is effectively detect and shut down erroneous stabilizer commands for the FCC. And basically, as much as we can fix the cheese, but like there are sometimes ways there are new holes that we might not detect, which is why there's our little mouse that yeah, it's a little mouse that's like basically like, ooh, gonna make some more holes in the system, and then like once there's a hole in the new cheese, there will be another total systems failure.